Okay, remember that when we last met, we talked about the idea of adding groups to the benzene ring and determining whether or not they cause the benzene ring to react react faster in electrophilic aromatic substitution. Remember that electrophilic aromatic substitution, I'm going to take a benzene ring, I'm going to add my electrophile to that, and ultimately I'm going to end up substituting the electrophile for a hydrogen on the ring. So to make the ring react faster, we need to make it more nucleophilic, which means that if we push electron density into the ring is going to react faster. So that means we need an electron donating group, whereas if we withdraw electron density out of the ring, it's going to be less nucleophilic, which means it's going to react slower, and we need an electron withdrawing group for that. So here is a list of groups from number 1 to number 10. It's the first of many that I'll show you. And they are ranked according to number 1 all the way down to number 10. Hydrogen is number 5 because that's the baseline. So if we go through that, a nitrogen attached to the ring is more reactive, will be more reactive than an oxygen, which will react faster than a benzene ring, reacting faster than a R group. So what we call these is these 4 groups right here we called activating groups. The hydrogen then is our baseline, and on the other side we have halogens. Now halogens are going to deactivate the ring, meaning that the reaction is going to be slower. So everything on the right hand column here is an electron withdrawing group. So halogens will deactivate the ring, but not as much as carbonyls, C triple bond N, NO2s, and then finally NR3+, remembering the idea that if you have a nitrogen with 3 alkyl groups attached to it, which gives the nitrogen a positive charge, that it's not necessarily that is deactivating by induction, although it is. The big problem is I'm trying to react 2 positively charged species, and that's going to cause the reaction to be the slowest. So we have to know this. We have to know these arrangements of groups from number 1 to number 10. And that'll be part of an online quiz where you're going to have to list those groups from number 1 to number 10. But you're going to have to make sure that you memorize those because, as we saw last Monday, the reactions require that we know whether the group is activating or deactivating. So what we also found was that we're going to attach the group, when we attach a group to a benzene ring, then it is what is called the directing group. So in other words, this Y group is going to be the director. And as the directing group, it's going to tell the electrophile, do you go to the ortho position, the meta position, or the para position relative to me, being the director. And as we saw last week, if this was just random, we would say, hey, this is random, let's move forward, but it's not. What we find is that if you have an activating group, that the activating group will cause the electrophile to go to the ortho and the para positions. And we'll talk a little bit more about that in a few minutes. You get very little meta product with an activating group. So that means that groups with a nitrogen, with an oxygen, with another benzene ring, and with an R group, those are all going to direct the electrophile to the ortho and the para positions. Now, what also directs to the para positions are the halogens, bromine, chlorine, etc. They are deactivating groups, but they do direct to the ortho and the para position, and I'll talk about why that is in a moment. So activating groups and halogens all direct ortho and para, and so they are ortho-para directors. All the deactivating groups except the halogens basically direct the electrophile to the meta position. There's very little ortho and para products that are formed in this reaction. So these are going to be what we call our meta directors. Okay, so those are going to be all of the carbonyl groups, a C triple bond N group, an NO2 group, and remember an NO2 group looks like this. And then I'm going to leave out the NR3 plus because, to be honest, you have a very difficult time doing any kind of electrophilic aromatic substitution with an ammonium and NR3 plus group. Okay, so that's the reason why we have to know that chart. Okay. And then halogens turn out to be deactivating, but they do direct to the ortho and para positions. They're kind of the exception to the rule. Now, why? Well, if we're looking at why these groups direct to the ortho and the para positions, it all has to do with forming the resonance structure of the carbocation next to the group itself. So when you have a group that has a lone pair of electrons on it, again, that's going to be the nitrogen, that's going to be the oxygen, and that's also going to be halogens. So when there's a lone pair of electrons next to the plus charge, so in other words, I add the electrophile, in this case to the ortho position, the plus charge ends up next to that group. When it's next to that group, then what happens is I'm able to form a fourth resonance structure. You're usually always able to form these three resonance structures, which we wrote in class last week, but now I can get an additional fourth resonance structure because the atom that's attached to the ring has a lone pair and is able to donate that to form that fourth resonance structure. So halogens, while they're deactivating, have that lone pair, and that's the reason why they are directing to the ortho and the para positions. So this shows you that there are four resonance structures if I added the electrophile to the ortho position, and if I now add the electrophile to the meta position, then you can see that the plus charge, as I draw the resonance structures out, the plus charge is never next to the atom with the lone pair, and so therefore it cannot form that fourth resonance structure. So if I add ortho, and you'll see in a moment para, if I add the electrophile to the ortho position, then we can get the fourth resonance structure, which will be which will lead to a more stable intermediate, whereas if I add to the meta position, then I don't get that fourth resonance structure. So it favors ortho addition as opposed to meta addition, simply because the fourth resonance structure forms, and that gives me more resonance structures for the intermediate, which then gives me a more stable intermediate. And if we looked at this from the para position, again, the plus charge will end up next to the atom with the lone pair, which will then be able to donate that pair of electrons to form the fourth resonance structure. Okay. What about alkyl groups? Alkyl groups favor ortho and para positions because if I drew out all of the resonance structures for adding to the ortho position and then the meta and para positions, what you find is that I get 3 resonance structures regardless of where I add the electrophile, but when I add to the ortho and para positions, I end up with the plus charge next to the group. In this case, there's no lone pair to donate, but it does form a tertiary carbocation, okay, tertiary allylic, versus all the other ones being secondary. So the favoring of orthopara with an alkyl group is simply because it's able to form a more stable intermediate when the plus charge ends up next to the group. Okay. Now, what happens in the deactivating case? Well, if I write out the structure of the deactivated groups, things like a carbonyl, things like a C triple bond N, or even the N double bond O, the nitro group, I kind of bring all of these 3 and say, you know what? That's an X multiply bonded to a Y group, and in each one of these cases, the X is delta positive and the Y is delta negative. So this would be sort of a general structure. This is kind of a general structure of these 3 groups. So if I come over here and I draw my X double bond Y group, again, the most important resonance structure is the one that has the positive charge next to the group. So again, if I add the electrophile to the ortho position in this case, I'm going to form the plus charge next to that group. Before, that was a more stable intermediate. Well, in this case, what happens is, because that positive charge is next to a delta positive charge on the C double bond O or C triple bond N, or even a full-blown positive charge on the nitrogen, which is really bad, what I have is a plus charge next to a delta plus charge. And so that's going to make that structure unstable. That resonance structure is going to be unstable, and as you can see, I drew a big red slash through it, meaning that it's not going to form. So if we take a minute to just kind of step back here and think about, okay, why did the activating groups direct orthopara? It was because when you added orthopara, the plus charge ended up next to the group, and that was good because you could form a resonance structure to form a 4th resonance structure to make the intermediate more stable. Or in the case of an R group, an alkyl group, you formed a tertiary carbocation which was more stable. In this case, it's exactly the opposite. Putting the plus charge next to the group is bad. It forms an unstable resonance structure. So now I've only got 2 resonance structures. Before, when I added the electrophile to the meta position, I got 3. 3 was not as good as 4, but in this case, none of those 3 resonance structures turn out to have a positive charge next to the group. And so all 3 of those resonance structures turn out to be stable, which is good because now I'm favoring the meta position. So a deactivating group, all of which fit this general form, you get 3 resonance structures for meta, you get 2 resonance structures for ortho. Let's just complete this out. If you added the electrophile to the para position, eventually the positive charge is going to end up next to the delta positive charge of the carbonyl group or whatever X double bond Y group you're using. And so therefore, that resonance structure will not be stable, so I'm back down to 2. So it's exactly this yin and yang of organic chemistry. Putting the plus charge next to an activating group or a halogen that has a lone pair forms an additional resonance structure. Adding the electrophile to the meta position only formed 3. When it's a deactivating group, putting the plus charge next to the group is bad. And so therefore, meta forms more resonance structures. So this is the reason why we're ending up with more resonance structures adding ortho-para to activating, and more resonance structures adding meta to the deactivating groups. Okay. And then, of course, just to complete this, the halogens, even though they deactivate by induction, they have these lone pairs, and they can go ahead and donate that lone pair to the carbocation when we add ortho or para to form that fourth resonance structure. And so while they're deactivating, they look like an X group with a lone pair on it. Okay. All right. And then again, adding to the meta position only gives you 3 carbocation resonance structures. And again, adding para will give you the plus charge next to the halogen, which then allows the fourth resonance structure to be drawn. Okay. So the whole idea here is that these are the overlying reasons why activating is ortho-para directing, why halogens are the exception, and why deactivating groups direct to the meta position. Okay? All right. So now we're back to the chart. And notice this chart has who activates by what mode. And again, I will just point out that induction, if we exclude the NR3 plus groups, that induction is weakly activating. It is also weakly deactivating. Resonance is a much more powerful way to withdraw and donate electron density. This is just another chart that kind of has some other groups in here. So for instance, we'll do some problems here. I'll give you some homework problems showing you all the differences. But it's really important, I think, to remember that the activating groups, for the most part, look like this. And all of these do except the ring. And down here, with the exception of these groups, all of these groups are X multiply bonded Y groups. So you might say, well, what about an SO3H group? Well, SO3H looks like an X double bond Y. The sulfur's delta positive and all of the oxygens are delta negative. It's got a multiple bonds, so it's going to be deactivating. You might say, well, why are CF3 and CCl3, why are they deactivating? And quite honestly, that's because when you have a halogen attached to the carbon, what happens is that all of those electronegative elements make that carbon very delta positive. And so that very delta positive carbon is going to pull electron density out of the ring. So these are all going to be electron withdrawing groups, and they're fairly significant. And we've talked about NO2 versus and the NH3 plus, or this is also an NR3 plus group. Okay, so this chart just gives you a little bit more detail, but really what we're gonna, if I give you something that is kind of new, it's gonna fit either this group or it's gonna fit the X double bond Y group, so that you're able to tell, okay, it's electron donating or withdrawing. All right, so then we started to talk last week about, well, why do I need to know this chart? The reason I need to know this chart is because what happens when I want to do a reaction on a multi-substituted ring. So the first thing we have to do is say Br2 and FeBr3. what electrophile does that produce. And, you know, the way I'm going to do these lectures is I can put a lot of material into 50 minutes because nobody's stopping me to ask questions. But what I'll do is, for instance, here, I'll say, you know what? Stop the, and I'm going to say stop the tape, but, you know, stop the video and write down what is the electrophile that you get with Br2 and FeBr3. Okay? All right. So you're back, you've written it down. What is it? It's a Br+. So where is that Br+ going to go? Well, what we're going to do is we're going to compare the groups that are on the ring, and the group that is highest up on the chart, the one that is either most activating or least deactivating, but basically if you numbered the groups from number 1 to 10 on the chart, what group is going to do the direction, the highest one. So in this case, C double bond OOH is deactivating. So the NH2 being number 1 is going to do the direction. What is it going to direct the bromine to? It's going to direct it ortho and para. Where there's already a group at a position, that position is blocked. So now I'm just going to write my two products. And my two products are going to be adding the Br2 to the ortho position and adding the Br2 to the para position. And at this point, we're going to treat these as being equal. We'll modify that a little bit. Okay, so we're going to take the, first we have to figure out, step number 1 is going to be, what's the electrophile? Step number 2, identify the group on the ring that is highest on the chart. Group number, and then number 3, figure out where to add those, that electrophile. Okay, so again, here's my groups from number 1 to number 10, and I believe this chart actually has groups number 1 to number 10 listed vertically. Okay. All right, so let's do another problem. At this point, what I would suggest is stop the video and write the major product or products. And then when you're ready, go ahead and start it back up again and see if you were right. Okay. First step is, what is the electrophile? It's NO2+. Which one of these two groups is highest on the chart? The OCH3. It's an activating group, so therefore it's going to direct ortho and para to itself, but the para position is blocked. So I'm going to go ahead and I'm going to add the NO2 group to that position. Now you might say, well, what about adding over here? All right, let's go ahead and add over there. How many different products do I have here? Okay. What did you say? Those two are the same products. So you only need to write them once. So in other words, these two would give the same product. Okay. All right. So that's how we're going to do this. Now, I did not last week give you one of the caveats for doing electrophilic aromatic substitution on a multiply substituted benzene ring. And here is the caveat. So, again, what I would ask you to do is stop the tape and then tell me what is my electrophile and what group then on the ring is going to do the direction. So take a minute and do that, and then come back and we'll see if you're right. Okay, it's going to be a CH3+. I'm going to put that in quotes because that's not a stable carbocation, but that's what we're going to add to the ring. What is the group that's highest on the chart? It's a bromine. Yes, they are both deactivating, but which one is the least deactivating? It's bromine. So what kind of director is bromine? It's the exception to the rule. So it is going to direct ortho and para to itself. Now, what about this para position over here? Well, it turns out that there is one caveat to doing the addition, and that is the issue of sterics. Now, the first sterics that we are going to invoke 100% of the time is that we do not add an electrophile in between meta in between meta substituents or 1,3 substituents. And the reason for that is there's just not a lot of room to add any group in between a bromine and a nitro group. So we do not add in between 1,3 disubstituted groups or meta disubstituted groups. So in this case, I'm only going to get 2 products. I'm only going to get the CH3 added ortho to the bromine and para to the bromine. Okay. So we do not add in between meta substituents. I didn't talk about that last week, but it's something we have to adhere to. Okay, and that's all about sterics. So we're going to do that. We're never going to do this 100% of the time, meaning that we're never going to add in between. Okay. Now, what we ultimately would like to do here is I would ultimately like to give you a problem and say, tell me how you would synthesize this meta ethyl nitrotoluene, or sorry, ethyl nitrobenzene, sorry. How would you make this compound from benzene? And the first thing that we need to do this type of problem is we need to know how to add the 2 groups. So how would I add the nitro group to the ring? Again, stop, take a minute, write the reagents down, and then come back and see if you were right. How do we add the ethyl group to the ring? Again, think about that, and then come back, and we'll see if you are correct. Okay, HNO3, H2SO4, and here would be CH3, CH2Cl with AlCl3 or FeCl3. In other words, Friedel-Crafts alkylation. Okay. Now, the order of the reagents makes a huge difference. When I add the first group, it must direct the second group to the proper position. So take a minute here. Which one should come first? Should I nitrate and then add the ethyl group? Or should I add the ethyl group and then nitrate? What do you think? Okay. Well, since these are meta, I'm going to need to put the meta director on first, which means I'm going to need to put the nitro group on, And when I do these problems, I put the groups where they are in the final products to not confuse me. So I'm going to need to put the nitro group on, and then the nitro group is going to direct the ethyl group meta to it, since nitro is a meta director. So now I would say, okay, I'm going to do HNO3, H2SO4, and then over here in my second set of reagents, I'm going to use ethyl chloride and aluminum trichloride. So the order of adding the reagents is important. Okay. So here is another problem. So I'd say take a minute here to think about how you're going to do this reaction. How do we add the SO3H group? SO3 and H2SO4. How do we add the carboxylic acid group? Now, if this was in class, there'd be a lot of page turning, a lot of just looking at me giving up. So here is our first group that we have not explicitly said, how do you add a carboxylic acid group to the ring? So now we have to think about, well, okay, so I didn't lay that out, but we know how to do that from previous reactions. So let me give you a couple of hints. Number one, I know how to add a bromine to the ring. I also know that if I add magnesium to that bromine, I'm going to make a Grignard reagent. What do I add to that Grignard reagent to convert it to a carboxylic acid? So I'm going to have my then H plus H2O step. What reagent should I use? If you said CO2, you were correct. Okay. So that's one way. One way to put a carboxylic acid group on a ring is to put a bromine on there. Oh, I forget. How did I add the bromine? Remember, Br2 and FeBr3 or AlBr3. And then magnesium to form the Grignard, and then CO2, and then H plus H2O. So that's one way to put the carboxylic acid group on the ring. There is another. Let's, for the sake of argument, say I want to put a methyl group on the ring. Once I put a methyl group on the ring, I can convert the methyl group to a carboxylic acid. Two questions here. How do I add the methyl group to the benzene ring? Friedel-Crafts alkylation. How do I oxidize the CH3 to a C double bond OOH group? Hint, we all did this in lab. It's purple. KMNO4. So here's two ways to convert or to add a carboxylic acid group to the benzene ring. So these series of reactions you're going to have to learn, because these are the ways that we're going to add those groups onto the ring. Right? We still have the issue of, in this case, these are meta groups. And so being meta, it doesn't matter in this case which group I add first, because the SO3H group, as you saw earlier, the S double bond O OH group looks like an X double bond Y group, which means that it is deactivating meta director. And the C double bond OOH group, a carbonyl, is also deactivating. So it really doesn't matter. I would put the carboxylic acid group on first. So I would convert the benzene ring to the carboxylic acid group, or I would add the carboxylic acid group first, simply because it's not as deactivating, so the second step isn't going to require as much heat as if there was a really deactivating SO3H group on the ring. So I would add the COOH group first, and then I would use the SO3H2SO4 to add the SO3H to the benzene ring in the second step. So you could use either method 1 or method 2 to add the carboxylic acid. Now, don't think in the future you can just put a 1 or a 2 there. You're going to have to write the reagents that you would use out to add the carboxylic acid. But my point here is that there are going to be groups that we need to know how to add, and they cannot be added in one single step. Okay. So carboxylic acid groups are the first one. So if you're making 3x5 cards, adding C double bond OOH, adding carboxylic acid groups to the ring, either one of these two methods would be fine. And you probably should know both. Which leads us now into the next section. Now, the next section of what we're going to talk about is actually in another chapter of the textbook. So you don't have to do those problems right now. If you do, that's fine, but we'll count those when we get to that section of the textbook. Namely, we need to go to the amine section. So the first thing is, we've learned that an NH2 group is the most activating, but how do you add an NH2 group to the ring? Well, you're going to have to use a series of steps. The first thing that you're going to have to do is to basically take your benzene ring, and you're going to need to add an NO2 group to it. So you're going to use HNO3, H2SO4 to this to add the NO2 group. Then what you can do is then you can reduce. Remember, reduce means add H in organic. So then we can reduce the nitro group to an amine by using iron or tin and HCl and heat. So either one of those metals will convert the nitro group to an NH2 group. So how do we add an NH2 group to the ring? We add an NH2 group to the ring using a reduction of a nitro group, which means that we needed to have the nitro group added first. Okay, so that's the third reaction that we need to learn in order to make add an NH2 group to the ring. We've already done the preparations of benzoic acid, right, in the previous slide, so you can go ahead and fill that in here if you would like. I'm going to skip the reversible reactions and come back to that in a moment. Now, the other way to add a whole variety of groups is to use what's called a diazonium salt. Now, the diazonium salt is an N triple bond N with the N having a positive charge that's attached to the alkyl group, and then there is a counter ion chloride that goes along with that. And so this is the diazonium salt. It's a salt because it's got a chloride counter ion. How do we make this diazonium salt? Well, what we do is we take our amine and we add to it HCl and sodium nitrite. Okay, NO2 is nitrite, not nitrate. So we add HCl and nitrite, sodium nitrite, to the amine, and we make the diazonium salt. You could do this with a regular run-of-the-mill alkyl group, but they tend to be explosive, so we're probably not a good idea to do that in the lab. On the other hand, aryl diazonium salts are really stable, and they are very good intermediates to use in synthesis. So for instance, if you took this aniline, that's the common name of this is aniline, and we just learned how to make aniline by nitrating the ring and adding and reducing it with iron or tin and HCl and heat to the amine. If you react that amine with HCl and sodium nitrite, you make an aryl diazonium salt, which you don't have to worry about blowing up because they're really stable. Once you make that aryl diazonium salt, you can do lots of things with it. So again, just to go back, how do you make this diazonium salt? You, first of all, start with benzene. You put the nitro group on the ring with HNO3, H2SO4. Then you reduce the nitro group with iron or tin to produce the amine, and then you react it with HCl, sodium nitrite, to make the diazonium salt. Once you may have the diazonium salt, you can do a lot of different reactions with that. And so the first one is what's called the Sandmeyer reaction. So Sandmeyer reactions are when you take the diazonium salt and you add a copper salt to that. That salt could be copper chloride, it could be copper bromide, or it could be copper cyanide. Now the cyanide is actually the most important of these, simply because that will allow us to add a C triple bond N group to the benzene ring. And so that the way to do that is using this Sandmeyer reaction. So, you know, if you, hopefully you got a stack of 3x5 cards with you, because we're going through them quite a bit in this particular lecture. What can I do with those diazonium salts? Well, okay, here's 4 more 3x5 cards. If you react it with H3O plus, you add the OH group to the ring. That's important. Can you add fluorine to the ring? Yes, using HBF4. Can you add an iodine to the ring? Yes, using potassium iodine or sodium iodine. Can you take the diazonium salt off the ring? Yes, using H3PO2, which is a really weird reagent, but that would replace the diazonium with a hydrogen. So diazonium salts are going to let us make a whole bunch of new or add a whole bunch of rings, compounds to the ring, groups to the ring that we couldn't before. And the whole idea here is that if you go back to our original chart, I'd like to be able to add every single group to that ring. And so I've got most of the reactions for most of them now. Now, just as a kind of an aside here, diazonium salts can also be used to make what are called diazo dyes. And I'll show you some examples. You've used these in general chemistry lab. So diazo dyes are when you take your diazonium salt, you can actually draw a resonance structure where you put the positive charge here on the end of the N triple bond N. And so what now this whole thing is my E plus. You can react that as an E plus with an activated benzene ring. The activated group is going to be an ortho-para director, but here's the second case where I'm going to introduce the idea of sterics. And what I'm going to say is to add ortho is probably not going to happen simply because there's too much steric hindrance between the activated group and this huge ring that I'm putting on. So that means I'm going to add that to the para position. And so when I add this entire E plus group to the benzene ring, I'm going to get that. And that is called a diazo dye. Okay, so that's another reaction we can do with the diazonium salts. Diazo dyes make excellent acid-base titration reagents. So for instance, if you've ever done an acid-base titration with methyl red, this is the structure of methyl red. It actually changes color when it's protonated, but notice it has that diazo group in it. And then here are some other diazo dyes that have different colors, some orange, some deep yellow, yellow red, deep red. A lot of this depends upon the groups that are attached to the benzene ring, and maybe we'll talk about the reason for that in the future. All right, so last thing I want to talk about here is to go back in my notes to what's called blocking. So it turns out that if you sulfonate, if you add a sulfonic acid group, this is the sulfonic acid. If you add a sulfonic acid group to the ring, you can actually take it off. So you could add a sulfonic acid group to the ring and then remove it using steam. Why would you want to do that? Well, this leads to what's called blocking strategies. So for instance, let's say that you want to take benzene and you want to make orthobromotoluene out of it. You want to make that in the highest yield possible. Well, in order to do ortho and para, to make the ortho product, we'd have to decide what group do we want to add first. You could make the argument it doesn't matter, but I would definitely add the methyl group first because that's going to make the second step react faster. Why is it going to react faster? Because the methyl group is an activated group. So the first thing I would do is I would say, okay, let's add CH3Cl, AlCl3 to that benzene ring. And then you would say, well, let's go ahead and add Br2, FeBr3 or AlBr3. But now the problem is I would get both the ortho and the para products. At this point, you might say, would they be 50-50? And the answer is probably no. Why? Because adding the Br plus next to the methyl group is not going to be as sterically favored as adding it para. So this is probably going to have some steric hindrance to it, which is going to reduce its yield, and most likely then that would be your major product. That's not the product I want to make. So what I'm going to do instead is I'd like to block the para position and force the bromine to go ortho. So here is how we would do that. We would take our toluene and we would add to it SO3H, H2SO4. Now I can invoke sterics here and say SO3H is a huge group. It's going to be very difficult for it to add ortho, so my major product of that reaction is going to be para toluene sulfonic acid. Okay. If you're having a moment of deja vu, that's simply the precursor to a tosyl chloride. Now when I add my Br2 FeBr3 to this, what's going to happen is I force the bromine to add ortho to the methyl group. So I guess I should have come back here and said, what kind of group is that? That's an activating, that's an activating ortho para director. Down here of methyl and SO3H, it's not SO3H, I know isn't on the chart, but CH3 is activating, SO3H is deactivating, so this is going to be the director, and that's going to direct the bromine to the ortho position because the para position is blocked. Now if I would like to get rid of the sulfonic acid group and go ahead and make my final product, all I do is treat that with steam, and the steam will strip off the sulfonic acid group and leave that ortho-para-toluene as the major product of the reaction. So this is actually what is called a blocking strategy. And we'll talk more about this in terms of syntheses of benzene rings. Okay, so I am trying to limit myself to 50 to 55 minutes for these lectures, so that way I'm not overwhelming you. And I understand these are concentrated, so by the time you work through them, and if you truly write out the products of the reactions, then you'll see that it's probably going to be a little bit more than 50 minutes, but that's just the nature of how this is going to work. There will be an online quiz that you will take after watching this video. Note that there are no pop-up quizzes in this video because I'm trying to get this one to you as soon as possible. But in the future, you may, where I said, hey, stop the tape and do this problem, you may have to stop the tape because a quiz is going to pop up and you're going to have to do that. So if you have any questions, I will be in the virtual office on Zoom on Monday, Wednesday, Fridays at 8, and Monday, Wednesday, Fridays at 1 p.m. I don't honestly care if you cross over and look at the 1 o'clock or the 8 o'clock one. Remember, those are just questions. You'll pop in, ask a question. You can hang out as long as you'd like. And I'll be giving you more details on that in an email to come later today. So I would like you to watch this video, which if you got to this point, you watched it, then do the online quiz, and then also read the textbook or skim through the textbook, the sections that I've given you, as well as then I would think it would be prudent to start the problems that are in Top Hat that go with those sections. Okay, so this is video number 1. I hope I haven't overwhelmed you, but this is our new normal for the rest of the semester. So again, if you have suggestions on how to make this better, by all means shoot me an email and I will take those under consideration. Okay, so we'll see you for the next video.